Have you ever wondered how modern concurrent collections like ConcurrentHashMap manage to be so fast? How they handle millions of operations per second without collapsing under the weight of locks? The answer lies in something called lock-free programming, and at its heart is the tiny but mighty instruction called compare and swap. This instruction is so powerful that it forms the foundation of almost everything in Java.util concurrent package. And today we are going to understand exactly how it works, when to use it, and why it's often faster than traditional locks. But also we'll uncover its limits because even CAS isn't perfect. So let's jump in and demystify atomic variables. In our previous episodes, we covered intrinsic locks with synchronized and explicit locks with reentrant lock. Both are blocking mechanisms. When a thread tries to acquire a lock that's already taken, it gets parked and the OS schedules something else. That's fine for coarse-grained tasks, but for fine-grained operations like incrementing a counter, it's an oracle. Today, we are going to move to the other end of spectrum, lock-free programming with atomic variables. We'll start with a quick recap of why locking can be a bottleneck, then introduce a compare and swap operation, explore all the atomic classes that Java offers, and discuss when you should reach for each tool. So grab your coffee and let's jump in. Let's remind ourselves how locks work. When you use synchronized or a reentrant lock, you are taking a pessimistic approach. You assume that conflicts are inevitable. So you force every other thread to wait while one thread holds the lock. The JVM hands this off to the operating system, which suspends the waiting thread. That's a context switch. Switching from one thread to another can take microseconds, which is an eternity in CPU time. Even if there is no contention, acquiring and releasing a lock still has some overhead. And there are other problems. Priority inversion, where a high priority thread waits for a low priority one. Deadlocks, if you are not careful, and if a thread holding a lock gets stuck, everyone else waits forever. That's why for simple operations like incrementing a counter, locks are like using a sledgehammer to crack a nut. But what if we didn't need locks at all? What if we could update a shared variable without ever blocking another thread? That's exactly what compare and swap or CAS makes possible. Let's see how. CAS is a single hardware instruction that does three things in one atomic step. It reads a memory location, compares it to an expected value, and if they match, writes a new value. If they don't match, it does nothing but tells you it failed. No locks, no context switches, just a quick check and update. Let's look at a classical example, incrementing a counter with atomic integer. Let's see what happens under the hood. It does a loop. Read the current value, then calculate the new one and call compare and set. If someone else changed the value in between, the CAS fails and loop retries immediately and thread never sleeps. It just spins until it succeeds. That's why it's called lock free. At least one thread is always making progress. And because it stays in user space, There is no kernel involvement, no scheduling overhead, just a handful of CPU cycles, and this is a game changer for high throughput systems. Java gives us a whole toolbox of atomic classes, grouped by what they do. Let's walk through each one of them quickly. So the first is scalar group. It involves atomic integer, atomic long, atomic boolean, and atomic reference. They handle a single variable of a primitive or object type, perfect for counters, flags, or swapping immutable objects. Second is the array group. It involves atomic integer array, atomic long array, atomic reference array. They let you update individual elements of an array atomically without locking the whole array. Great for parallel processing where each thread works on different index. Third is the field updaters. It involves atomic integer field updater, atomic long field updater, atomic reference field updater. These use reflection to atomically update volatile fields of existing objects. They avoid the memory overhead of wrapping each field in an atomic object. They are used internally in high performance collections like ConcurrentHashMap. The fourth is the specialized reference group. It involves atomic stamped reference and atomic markable reference. These two classes solve the ABA problem where the value changes from A to B and then back to A, but the CAS doesn't notice. By adding a stamp or a mark, you can detect those intermediate changes. The fifth and the last one is accumulators and adders, which involves log adders, double adder, long accumulator, double accumulator. Under extreme contention, even CAS can suffer as we have seen because many threads spin up on the same variable. These classes use a technique called cell stripping. Each thread updates its own private cell and the total is computed by summing all the cells. That reduces contention dramatically and can outperform atomic long by an order of magnitude. Each of these families has a specific use case and we'll deep dive into each one in later episodes. But for now, you have a map of a territory. So, are the locks dead? Absolutely not. There is a catch and it's a big one. And here is the chart of trade-offs. Atomic variables are amazing for simple single variable updates, but they have limits. If you need to update multiple variables together, like transferring money between two bank accounts, you can't do that with a single CAS. You need a lock to ensure both changes happen atomically. Also, if your critical section is large, doing I/O or complex calculations, spinning a CAS loop would be a disaster. It's better to block and let other threads run. And here is the kicker. Under very high contention, CAS can actually be slower than locks. When hundreds of threads hammer the same counter, most of them will fail their CAS and retry, burning CPU cycles without making progress. Locks, on the other hand, put waiting threads to sleep, freeing up the CPU for others. So it's a trade-off. Low to moderate contention, CAS shines. Extreme contention, locks might be better. The key is to measure. Ask yourself how many threads will access this variable. Is it a metric counter that gets updated thousands of times per second or a business state that changes infrequently? That will guide your choice. Now you must be thinking, why does CAS even exist? Modern processors have built-in instructions like compare and exchange on x86 machine or load linked or stored conditional on ARM processors. They provide atomic read modify write at the hardware level. The JVM uses these instructions directly. It inlines them into your code so you get near native performance. Let's walk through exactly what happens when thread A on core 1 and thread B on core 2 both call atomic integer increment and get method, and the initial value is 5. Our atomic integer lives at a specific memory address, and right now it holds the value 5. Both CPU cores, core 1 and 2, have this value sitting safely in their L1 caches. Neither thread has done any work yet. Both thread A and thread B execute the get method part of the operation at virtually the same instant. Thread A reads the value 5 and calculates 6. Thread B does exactly the same thing. It reads 5 and calculates 6. At this moment, both threads believe they are about to win the race. They both have their expected value set to 5. And the race begins. Both threads now fire off the hardware compare and exchange, or you can say compare and swap instruction simultaneously. They both ask the CPU hardware if the value at this memory address is still 5, swap it to 6. And then hardware decides a winner. The CPU hardware steps in to handle this collision. Even though instructions by both the threads happened at the same time, the silicon arbitration logic picks a winner. Let's say thread A wins this micro race. For thread A, the hardware locks the memory bus or the specific cache line. It checks the memory location, confirms it's 5, and atomically swaps it to 6. Thread A gets a success response and immediately moves on to execute its next piece of code. The memory is now officially 6. Core 2's cache line becomes invalid. Core 2 must reload the value from main memory now. Thread B's CAS instruction arrives just a fraction of nanosecond too late. The hardware checks the memory location of thread B, but it sees the value is now 6, not the 5 that the B expected. Because the values don't match, the hardware fails thread B's CAS operation. The hardware does not write anything. It simply returns a false or fail status back to thread B. And this is the most important part. In the locking world, thread B would now be put to sleep by the OS, causing a heavy context switch. But with CAS, nothing bad happens. Thread B stays awake and running in user space. Instead of panicking, it looks at a failed result and says, okay, someone beat me to it, no big deal. Thread B immediately executes next iteration of its loop. Since its CAS just failed, it knows its old copy of data is stale. So thread B does a fresh get on the atomic integer. It reads the memory location again and sees the new value or the correct value, which is 6. Thread B adds 1 to it, calculating the new target value 7. Thread B now fires off another CAS instruction. If the value at this memory address is still 6, swap it to the 7. This time, no one else is fighting over the memory. The hardware checks the memory, confirms it is still 6, locks the cache line, and atomically swap it to 7, and returns a success to thread B. And here is the final result. Thread A successfully set it to 6, thread B failed once, spun back around and successfully set it to 7. The entire ordeal from the initial collision to thread B's successful second attempt took a handful of CPU cycles, like nanoseconds. Thread B never called the operating system, never went to sleep, and never gave up the CPU. It just retried instantly and got the job done. That is the raw power of hardware supported compare and swap. In fact, almost every class in java.util concurrent relies on CAS somewhere under the hood, from ConcurrentHashMap to semaphore. It's the foundation of Java's concurrency toolkit, and because it's lock free, it's immune to deadlocks, priority inversions, and that's huge for systems where reliability is critical. Alright, let's wrap it up. Today, we connected the dots from locks to atomic variables, cracked open the compare and swap operation, and explored the 5 families of atomic classes, and most importantly, learned exactly when to use each one of them. But here is the thing, this is just the beginning. In the next episodes, we are going to take deep dive into all the 5 families of atomic classes. So stay tuned and thanks for watching, and I'll see you in the next one. If you found this video helpful, please give it a thumbs up and subscribe for more technical content.